Also herzlich willkommen, liebe Kolleginnen und Kollegen am Geozentrum und am LIAG sozusagen, WDR. Da sehe ich einige Kollegen, aber wenn ich hier drauf gucke, sehe ich vor allen Dingen auch noch Kollegen vom DESMAX-Projekt und das bringt mich direkt zu Raphael Rochlitz, der heute auch den Vortrag halten wird. Raphael ist, ich glaube, eigentlich in jedem LIAG-Seminar mittlerweile vertreten, insofern gern gesehener Gast. Und für all diejenigen, die ihn noch nicht kennen, sind ganz kurz 2 Worte, Raphael, bevor du loslegen musst. Ist quasi ein DESMAX-Urgestein, deswegen passt das auch ganz gut zu den DESMAX-Teilnehmern, die wir hier haben. Promoviert im DESMAX-Projekt 1, mittlerweile aktiv im DESMAX-Projekt 2. Darüber soll es in dem Vortrag heute auch gehen, nachdem wir in den letzten Vorträgen eher was zur Modellierung gesehen und gehört haben, geht es jetzt den Schritt in die Inversion, in die breite Inversion der Daten, die im DESMAX-Projekt erhoben werden, also die semi-airborne Electromagnetic-Methode. Und damit wünsche ich uns viel Spaß und Raphael, ja, dein Vortrag.
Okay, welcome everybody to my talk about 3D inversion of semi-airborne electromagnetic data with LIAG's open source tools cusTEM and pyGIMLi. Thank you for the introduction, Mike. So it was a very good summary. When I started at LIAG, I was mainly working on modeling and simulation of 3D EM data, and meanwhile inversion is the topic of interest. And I also want to acknowledge my colleagues, in particular Thomas Günther, Michael Becken, and Matthias Honska for processing data and having nice discussions about 3D inversion to achieve the progress we have. So at first I will talk about the data and the forward operator, which is kind of the motivation and the basis for our 3D inversion. Then I will shortly introduce our inversion approach, and more interesting probably for the audience is a synthetic case study I will present, where I will invert a synthetic data set with flat topography and the real topography, and we can investigate the differences that occur. And finally, I will also present a real data inversion for our Schleiz field. So our DESMAX project, we collect semi-airborne electromagnetic data. And in the beginning, we started with helicopter-towed receivers. So here you can see the BGR receiver system. In this bird, there are 3 induction coils installed, measuring the 3 components of a magnetic field. And on the surface, we installed grounded dipole transmitters, injecting an active source current. And yeah, this is the geometry here in a sketch. So we have basically a transmitter, which is like a 2 kilometer long electric dipole. The transmitter injects currents into the subsurface. The currents flow through the subsurface and they induce magnetic fields overall in the subsurface. And in particular, characteristic are good conductors, which lead to signatures in the magnetic field pattern if we fly with our receiver system above the subsurface. We could also install some ground stations, for instance, magnetic field receivers or electric field receivers at the reference, as a reference for the airborne data. And what we're interested in, of course, are the conductivity changes of the subsurface, which are good indicators for saline water and groundwater interfaces, or also for mineral deposits. So in DESMAX, the targets of investigation are related to mineral deposits mainly, and in our LIAG surveys, we are more interested in ground and saltwater interfaces. And yeah, a particular challenge for simulating the data is that we need to include our topography, we need to include our realistic transmitter layout, and we could also consider anisotropy and IP effects. So this is not a standard EM setup, but a rather complex 3D geometry. Meanwhile, we are not only working with helicopters, we are also working with drones. So this is a photo from our most recent survey in Spain. It's only 2 weeks ago. Here we are looking for sulfide deposits near Sevilla, and we kind of install our receiver systems not at helicopters but on drones, because drones need less permissions to fly. They are kind of cheaper in doing surveying. More flexible. But we also see that we have rough terrain here, so it is quite interesting to see how the drone can be kind of flown over this terrain. So we need to set the correct height in our flight plans. This is a new research topic of interest, which is actually conducted. And another application of drones, this is a photo from Gießen, our test site here close to Hanover. Here we are looking for saltwater and groundwater interfaces, and this is the system with a sensor in the center. So these are our data, and basically the good thing is that we don't have any differences in our geometry between helicopter and drone measurements. So we can use exactly the same modeling and inversion codes, it's just on different scales. So we just exchange our helicopter with a drone, and for the drone measurements we also don't make use of surface receivers anymore, because the airborne data are meanwhile quite reliable, so we don't need reference stations anymore. How do data look like if we measure them? So this is a survey patch, a flight area. Here from helicopter data, we have a profiles of about 6 kilometer length and like 3 kilometer width. We have in the center our dipole transmitter, and our helicopter flies along lines. We can sort the data and arrange them by lines. And on these lines, we can look at our magnetic fields. On the right side, we see the real part of a vertical component and the imaginary part on the vertical component. So we are processing our data in frequency domain. That's why we have a complex magnetic field. And we also see quite nicely that our total magnetic field amplitudes decay with distance from the transmitter. So these are the magnetic field data which go into our inversion. The second ingredient we need for inversion is a good forward solver. And this is what I presented in the last LIAG seminars, the custom software. So we can consider the topography, the transmitter layout in a finite element mesh. We use unstructured grids to consider our topography, and we can calculate electric fields in the subsurface and on the surface, and also magnetic fields in the air. So this is quite well established, and the good thing is, due to the unstructured mesh approach, we can not only discretize kind of regular setups like here on the left side. So this is a mesh example from our Gießen test site. We have only a straight transmitter and a few shorter flight lines on a kind of flat topography. The good thing is we can also consider mountainous areas. So on the right side you see a mesh which is based on real survey layout in the Harz Mountains close to Goslar. Here we have installed 4 transmitters in valleys, so they are kind of crooked and not elongated anymore. They are also laid out over hills and Google valleys, and we have also irregular flight lines. So this is possible to consider with custom, and that's why we have all the ingredients for our 3D inversion. The inversion procedure itself deals with minimizing an objective function. So as an input we have the forward response of our conductivity model in the subsurface, and we have our data, and we have also a model update. And basically, we try to minimize this objective function in an iterative procedure. And the procedure we are using is a Gauss-Newton scheme, which is quite established in EM inversion, but also in other methods. And this Gauss-Newton scheme is already implemented in the well-known pyGIMLi library, which is programmed by Thomas Günther and colleagues. So I think you all heard about pyGIMLi. Meanwhile, we have this Gauss-Newton scheme and the minimization procedure in an object-oriented environment. So what we need to supply is a forward response, which is already available in custEM, and the Jacobian matrix. The Jacobian matrix contains entries, derivatives of our model parameters after the data. And this Jacobian matrix provides the information in each iteration step in which direction our conductivity model should be updated. So if cells should be more resistive or more conductive after a certain inversion step. And yeah, this is actually the main challenge, to provide this Jacobian matrix. There's lots of literature and there are many established approaches, for instance, by these authors. Most of them use finite difference discretizations, which is a bit different to the finite element method I'm using. And that's why we had quite some implementation challenges. We need to implement all the algebra, we need interpolation matrices, we need to think about efficient parallelization and ordering, because our Jacobian is kind of 5-dimensional, because we have multiple flight areas, we have multiple receiver positions in each flight area. We can have different combinations of electric and magnetic field components. We can have multiple transmitters, and of course we have multiple frequencies in a range of 1 to 10,000 Hertz. It's also pretty dense and large, so Jacobians can easily reach this size. And yeah, such a Jacobian needs like 100 gigabyte of RAM in our memory. So we need to think about efficient computing, and this is what I was dealing in the last year. But meanwhile, we can handle this procedure, and that's why we can continue with our results. The first case I want to present is a synthetic inversion. I have already shown you this setup. This is from our Goslar survey close to the Harz Mountains. And if we want to find a nice conductivity model for our data, we need to think how to discretize our subsurface. And we decided, let's go to the right side first, to let every cell be an inversion parameter. So every cell can get a unique conductivity value and can be updated in the next inversion step. We can also include our transmitters here, which are the real transmitter positions of our survey. The flight lines I have added here for this synthetic case are just laid out around the transmitter. So these are not the real flight lines, but they are kind of related to the real flight lines. But the topography and transmitter information is the same as in our real survey. And around our inner inversion mesh, we have also an outer inversion mesh, which kind of helps to let conductivities, which are different in the inner part, let the conductivities fade out to a homogeneous half-space model, which needs to be applied around our inversion mesh to avoid simulation artifacts in our forward modeling. For the test case, I have included 4 different anomalies in the subsurface. So here on the right-hand side, you can see the attributes of these 4 anomalies. The purple one is a resistive anomaly, a quite large brick. When we have a highly conductive thin plate, kind of vertically dipping, we have another semi-conductive target, the green one here, and we have another semi-resistive target on the right-hand side. And on all our flight lines, we record BX, BY, and BZ airborne receivers. And we also installed, it's bit difficult to see 11 ground stations as in our real survey layout on the subsurface. So we have here a few ground stations and almost 1,000 receiver positions in the air. And for the synthetic data set, we consider 12 frequencies between 6 and 3,500 Hertz. And we add a Gaussian noise of 5% to our synthetic data. And the Jacobian matrix has these dimensions. So I already talked about it. They are quite large. It's about 100,000 times 100,000 if we have a bit more data. So these are the scales we are dealing with. And now we can invert our synthetic data set with a mesh that includes the topography. So if we consider the real topography, we can see that our resistive, this is the highly resistive anomaly, the highly conductive anomaly, semi-conductive, and oh, I need to think about it. Oh no, so sorry, the anomaly 4 is also conductive with respect to the backbone resistivity. So this is the less conductive anomaly, but we can see that they are nicely recovered, and that also the depth of the anomalies is nicely recovered. We have also a good RMS midfit at the end of our inversion. So this looks quite nice. Now, on the right-hand side, you see an inversion result where I just use an average height as topography, like in almost all final difference codes that exist so far. So if we do not consider the real topography here in this area, we get lots of artifacts, in particular at the surface. We can still see the main conductors, all 4 of them actually, but we also see many other conductivity variations which are not valid, obviously. And now we can have a look through our conductivity distribution in more detail. So at first, I will show only isosurfaces of conductivities between 10 and 50 ohm meters. So these are the most conductive areas in our model. And topography case, well resolved. On the right-hand side, we already see that there are some conductors where none should be. And now we include some higher resistivities, up to 100 ohm meters. So basically the same feature, very well resolved in our topography inversion, and more artifacts in our flat topography inversion. I have 2 more steps. This is with 250 ohm meters. So in the background of 1,000 ohm meters, this is 250 is still kind of a conductor with respect to our background model, and we see that the kind of larger conductor is formed here where none should be. And also the surface artifacts start to appear here, and also this anomaly on the right hand side is increased to greater depths. And now we include also highly resistive values. So conductivity is up to 250 and higher than 2,000 ohm meters. And I think it's quite clear that we need to consider the topography to recover all anomalies nicely. If we don't do it in cases like in Goslar, where we have steep topography, we will run into artifacts. That does not mean that it is impossible to invert data with topography without considering it, but I think there's it is problem dependent. So if the topographic variations become too high, I think we really need to consider a full 3D inversion with unstructured bits. This was the synthetic case, and now let's switch to real data. So the data set I'm talking about was measured in 2016 and 2017. This was our first survey area from the DESMAX project in Schleiz, in Thuringia. Here we can see a geological map of the main geological units. So we have mainly Silurian, Devonian, and Ordovician rocks in the Berger Anticline. And the BGR has already conducted some airborne measurements with a resolve system in this larger blue area. to identify the most suited target for our semi-airborne experiments. And if we look at the resource system conductivity distribution at the surface, we identified this southern part of the blue area to be the target of interest for our semi-airborne experiment. And we ended up with 8 flight areas in this red subpart, the southeast of flights between Thuringia. Here's already Saxony. We have a long profile of reference data with 2D methods like ERT and LOTEM. And we focus now on the central flight areas, which are located around TX1, TX2, TX11, 12, and here should be a TX13, so it's missing here. On the right-hand side, you see the connectivity distributions of the 2D results. So this is the helicopter EM results with the smallest penetration depth. Here are our semi-airborne data inversion results on the main profile, but only a 2D or 2.5D inversion with Mare 2D EM, so no 3D inversion so far. We have a ERT reference dataset and the LOTEM dataset, and overall we see that the main conductors appear at the same positions, but we also see that there are differences in the 2D results. And if we look at the geological map, we can also see that, in particular due to this northwest-southeast striking fault, we have real 3D geometry, and that's why it is quite interesting to analyze these data now in 3D. At first, I started with a subset for first comparisons. So this is, I will go back. This is only this smaller part here from our complete data set. We picked 4 flight lines for the transmitter 1 and transmitter 2. And this is how our data look like. So we invert X components of our magnetic field data and vertical components. So this is actually not the X component, but a kind of rotated X component. So X points in the direction of the flight lines. And we have a 2-component data inversion for both transmitters. So we have the same flight lines covering transmitter 1 and also covering transmitter 2. And overall we have, I think, 12 frequencies used between 7 Hertz and 1000 Hertz. And this is the inversion result below all the 4 flight lines. And to compare and validate my 3D solution, we use the Mare 2D EM code. So again, 2.5D inversions of each flight line separately. And in cusTEM, we have the full 3D inversion of all lines together, but we look at them one after each other. And line 6, I will go back. Line 6 is in the northern part, line 9 is in the southern part, so that you can locate the conductivity profiles. And we do see some changes between the flight lines. We also see them in 3D. What we also notice is that the left-hand part of our conductivity model fits very well between 2D inversion and 3D inversion. So we have almost the same conductivity values also of the background. We have the conductors at the same location, but if you look on the right-hand side, we see that the 2D inversion is producing a way more resistive, deeper subsurface, and also the anomalies are larger, and also with a stronger conductivity contrast with respect to the background, compared to the 3D inversion, which kind of looks a bit smoother. So now it's the question, why do we see these differences? And if we look at our 3D inversion result in 3D, we see that the left part of our model is also, it looks quite two-dimensional also in the 3D result. But the right part of our survey area looks rather three-dimensional because this conductor is located only on the surface below flight lines 8 and 9, but it's kind of filling a larger volume towards northeast at flight lines 6 and 7. So here we have a real 3D structure, and that's why, of course, our 2D and 3D results differ. And if you also consider our geological map in this area, so our flight lines are located like here. This is the line 7 on the main profile. You see that this fault is approaching closer to our profile on the eastern side, and that's why also our 3D structures approach our main profile, and probably our 3D inversion is here more reliable than the 2D inversion because of our 3D geometry. Following up, to show that it is really 3D target, here I have shown the 3D inversion result of all 4 flight areas, so TX1, TX2, TX11 and TX13. It's a 13 kilometer long area times 4 kilometers in the south direction. It includes like 1,000 receiver stations, all in all, no more, 2,000 receiver stations with 2 components for 4 transmitters. So this is a real multi-flight area data set, a large data set. And this is the kind of combined inversion result if we put all our data in a single inversion. And to show you that it is also reasonable, what I have shown you before. So the conductivity distribution is kind of reliable, I think, because we have a very good data fit. I have shown it here for the line 7. So this is again the profile in the center of our survey area, color coded. We have the 4 transmitters, orange, red, purple and gray, and where we see the sign reversal in the center, our transmitter is located. So this would be the location of transmitter 1, transmitter 2, transmitter 3, transmitter 4. We have again real parts, we have imaginary parts, the Z component and horizontal component. And this the most important thing is here I'm comparing the data with our final model response. So if all these points lie over each other, we have a very good data fit, and basically we see that this is almost the case everywhere along the profile, and we even see that our inversion model is able to handle some kind of single points with different signs in the imaginary parts. So our data fit is really good for the 3D inversion we got. And now I want to shortly comment on the geological information we have here. So we have already seen that we have black shale conductors in purple, which are on the northern side of our fault and which are also particularly located on the southern side of the fault. So there's the C1, C2, C3, C4, C5 conductor. But the main conductors are C1, C4 and C5, and if we compare it with our transmitter locations, we see that the C4 conductor at the surface is very well recovered, also the C1 conductor, also the C5 conductor, and in a more regional scale, we see a quite nice distribution between a difference between the southern part of the survey area and the northern part, which are divided by this northwest-southeast dipping fault. And in transparent, Thomas has plotted the occurrence of Devonian rocks on top of our connectivity model. So we have this darker anticline striking in this direction, and we have the northwest-southeast striking fault here. And in the southern part, we have Ordovician rocks, and on the right, on the left, and in the north, we have Devonian and Silurian rocks. And it's quite interesting that we even see regional scale geology in our semi-airborne data because the profiles are so large. And the Ordovician rocks are more resistive. That's why this area is mainly blue, despite this C4 conductor. And on the left, north, and on the right, we see very well the occurrence of the black shales at the surface. And of course, we are not only interested in the conductivity distribution at the surface. We are interested in the conductivity distribution with depth. And this is something that is work in focus to analyze our 3D results in comparison with the results from Annika Steuer. So the 2D results on the profile I have shown below. This is what we want to do now, and after that, publish this test case in our inversion method. Now, you might ask, how expensive is it to run 3D inversions with cusTEM? This is a computational statistic table I have prepared. So in our synthetic test case, we have a mesh with 50,000 nodes. We need all in all almost 2 days on 60 cores in our workstations. We need like 1.2 terabyte in total. We have like 6 hours computation time per iteration. And the main effort is actually the back substitution time. So for each receiver point, for each data point, we need to calculate a back substitution of our finite element system of equations. This is due to the nature of explicit sensitivity calculations. And this is quite interesting because usually people say that the forward solution is the bottleneck in 3D inversions, and for our data sets, and this is particular due to the nature of semi-airborne geometries, the back substitution time becomes the bottleneck. The small slides part inversion require only 40 minutes per iteration and only 8 hours. So I think it is quite reasonable to extract subparts of our data to do some inversion tests in specific areas before running larger combined inversions, which was done in the end. The combined inversion has kind of a similar dimension as the synthetic case and require also almost 2 days with a terabyte of RAM. So what do we want to do now? We need to improve the implementation of our pyGIMLi and cusTEM inversion framework. So basically everything works, but we want to program it more comfortable also for external users. We need better error models for our helicopter and UAV-based semi-airborne datasets. So for now, we mainly use a constant error of 5% and the absolute noise level, but it would be more. It would be better to have an error model based on our data processing. We also want to use our Jacobi matrix for resolution analysis to provide information in which areas our conductivity model is reliable and supported by the data. I have a few options in mind to speed up our inversion process, in particular for very big data sets, by a few factors. And of course, we could also consider alternative inversion strategies, maybe iterative inversion techniques, or there are a few options to continue. And to just show you which kind of data we have already acquired over the past years, we have multiple large-scale data sets with a similar dimension of our slides data set I have presented in this talk. So meanwhile, we have another helicopter data set in Kropfmühl, we have another helicopter data set in the Harz Mountains, we have a helicopter data set from Kiruna, and we have also drone data sets since last year from Namibia, which are kind of processed by the colleagues from the University of Münster. This is our survey from 2 weeks ago in Spain, which will be processed and inverted by colleagues of Münster and me. And as you can see, we have kind of one postdoc or PhD applied to handle these cases. And since cusTEM is now available with a 3D inversion, we can kind of reprocess existing data from 4 and 5 years ago, but we can also analyze our new data with a suited inversion tool. in the next month. So I hope that there will be many more 3D inversion results towards the end of the year. And final step in DESMIX 2 and DESMIX Real would be to not only invert control source electromagnetic data from our semi-airborne geometries, but also consider a combined inversion of 2D data, for instance, from low-temp surveys, from transient electromagnetic surveys. We have also natural source helicopter measurements in DESMIX 2. This is called the FMAC method, so we need also an MT inversion. This is work in progress. Markus Schiffler from the EPRT and me are working on this. This would be the final goal, to be able to put different EM data sets into a joint inversion for best possible geological analysis. And with that, I want to thank you for listening.